Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. So in this video I will explain about the last two topics in the electrostatic chapter. So let's look on the electrostatic potential energy first. When we connect a capacitor to a DC source, for example a battery for example, so basically the battery or the DC supply will be supply energy to the capacitor. So however, if we consider the dielectric material used in that particular capacitor to separate two conductor in the capacitor is a perfect dielectric, so basically there is no current will be flow inside that particular capacitor. So where does the energy supply by the DC source or the battery goes? So basically the energy supplied by the source will be stored in the dielectric, and that particular energy we call it as a electrostatic potential energy, and this particular energy is used by the capacitor. So in order to store a charge at both conductor exists in that particular capacitor. So during charge up the capacitor, so basically the potential across the capacitor will increase from 0 until certain level of voltage. So normally this particular voltage level will be same as the level of DC power supply or of a battery. At the same time, so the value of the charge will be increased. The charge that accumulating in the conductor will be increased from 0 until certain positive value. So this particular condition is occur on the conductor that connected to the positive terminal of the DC supply, whereas on the negative conductor or the other side of the conductor that connected to the negative terminal for the DC supply, the charge will be accumulating from 0 until certain value of negative Q by the fact that on that particular conductor the electron will be accumulating. So the potential difference of the battery the potential difference of the capacitor can be calculated by using this equation. So whereas V is equal to Q divided by C, the unit for this particular equation is in volt. The amount of work that need to be done in order to transfer additional charge dq in any conductor can be calculated by using this equation. So whereas dWe represent the work need to be done on the work need to be increased or add is equal to V. So this one is the potential of that battery multiplied by dq. So dq is represent the additional or changes in the charge value on the conductor. If we replacing this equation inside this expression, then we will have dWe is equal to Q divided by C multiplied by dq. And in order to solve this expression, so we need to integrate both part of it. Then we will have the work need to be done in order to transfer additional charge to the conductor is equal to integration from 0 until Q, so Q divided by C dq, and the solution for this integration is equal to this expression. So whereas in this case work is equal to half of Q squared divided by C, and the unit for this expression is equal to joule. Alright. So previously we have been derived the general expression for the capacitance. So whereas C is equal to Q divided by V, and this expression unit is equal to F, which is farad, the value for the capacitance, the unit for the capacitance. And by replacing this equation to the equation of energy that we just derived just now, then we will have another expression that represent our work is equal to half CV squared. and the unit is still in joule. At the same time, so we have been looked before, so we have C is equal to permittivity for the dielectric multiplied by the area of the conductor divided by the thickness of the dielectric material, and as well as the different potential is equal to E. So this one is the magnitude for the electric field multiplied by D. So D is the same as the previous D, which is the thickness for the dielectric. Then by considering these two expressions and replacing into this equation, then we will have the energy or the work need to be done is equal to half epsilon. So this one is dielectric permittivity multiplied by magnitude for the electric field squared multiplied by A and D. So this is area for the conductor. So this is the thickness for the dielectric. The expression we have here is actually almost the value of the capacitor. So therefore, we can rewrite the expression as this one. So whereas the WE or work need to be done is equal to half electric permittivity for the dielectric, magnitude for the electric field squared multiplied by the volume of the capacitor. If we consider this value of energy in terms of density value, so we will have the density of work or the energy stored in the dielectric is equal to half epsilon E squared, and the unit in this case is equal to joule divided by m the power of 3. Alright, so let's look on the last topic for this chapter. We call it as a image method. So let's consider, so we have one particle charge, and this particle charge is located above of a plane, a conducting plane, for example. So in this case, the conducting plane has been grounded, so that the potential along this conducting plane is equal to 0. So the distance between this charge and conducting plane, so let's say we take is equal to D, and this distance is measured on the Z axis. So the charge is located on the air. So in this case, the air has been represented by this permittivity value. So because of our charge is positive in sign or in a value, or in this charge is a proton, is as a proton. So basically we will have the direction for the electric field in this case is in this direction. So the problem is, how can we determine the potential difference and the electric field produced by this single particle charge? So in order to calculate the potential difference and the electric field produced by this charge, so we can use either one of these techniques. So the first technique or the first law, we call it as a Coulomb's law. In the Coulomb's law, so we need to define the magnitude and the location for this particular charge. And after we determine these two values, then we can put all the parameters that we know in this equation so that we can determine the value for the electric field intensity. So however, in this case, the magnitude for the electric charge is unknown, and the distribution of charge in this particular plate is non-uniform. So therefore, in this case, so we cannot use the Coulomb's law to calculate the electric field and as well as the potential difference. The second technique that we might consider is by using Gauss law. So in this Gauss law, so we can solve this this problem, in order to determine potential difference and electric field intensity value or expression, so by using this expression. So however, by referring it to this case, so the Gaussian surface, the Gaussian surface is unable to create. So therefore, so we cannot apply, we cannot solve that problem by using a Gaussian law. So the last technique that can be applied is by using Poisson and Laplacian equation. So whereas the Poisson equation is given by this one, so del squared V is equal to minus rho V divided by epsilon, and the Laplacian equation is represented by this expression. So whereas we have del squared multiplied by V is equal to 0 if we consider there is no free charge exists. So in order to use this equation, so we need to define the boundary case, or the boundary condition for this case. So however, the solution for the Poisson or Laplacian is quite complicated, and it might make us could not solve this in this particular problem. So in order to solve it, since we have this plate potential is equal to 0, so basically it almost similar like in this case, whereas so we have this is our original particle charge, and the value for this particle charge is a Q. So this is our 0 volt plane, and then it is like we have another charge here, almost similar charge, but in this case the charge value is equal to negative. So because we have two different sign of charge, so the almost same direction for the electric field will be developed similar like what we have here. But in this case, if we measuring the center of this separation distance between these two charges, so we will have the potential on this plane is equal to 0. The distance for this charge and the plane is the same as the distance of this charge with this plane, and this charge we call it as a duplication charge or image charge. So this method we call it as a image method. So based on this condition, so we can apply Coulomb's law in order to find our expression for the electric field intensity at any point. So let's say we are trying to find, so what is the value of E at this point, for example. The thing is, we need to make sure that the location of charge is symmetry. So that means that, so the distance between this plane and the charge and the positive charge, and this plane and the negative charge, it should be the same, so that we can have the potential difference at along this line that caused by these two charge is equal to 0. And if the charge reside in more than one grounded plane, so the image need to be established for every plane. And basically this technique, or we call it as an image method, also can be used to solve the problem that involve the charge that exists in the density value. For example, line charge density, surface charge density, and volume charge density. Alright, so in order to understand this topic, so let's look at one example. So let's say we need to find the expression for the electric field intensity at point of P, and the coordinate for the P given by x, y, z in a z greater than 0. And the E is caused by the positive Q located in a free space at distance of D above a grounded plate residing at z is equal to 0. So we have the case like this one. So we have a positive Q here, Alright, and this is our grounded plane. So the Q is located at distance of D here, and because of that, so let's consider, so this is our Z axis, and because of that we can estimate, or we can assume, the coordinate for this particular charge is equal to 0, 0D. So in order to solve this one, so we need to create another charge here. So the distance between the plane and the negative Q charge is the same as the previous one, is equal to D. And because of that, the coordinate for this negative charge is equal to 0, 0, minus D. So let's consider the position of our test point in this case is here. So we have P is equal to X, Y, Z, and we need to calculate the electric, or we need to derive expression for the electric field intensity in this test point. Then we need to determine, so for example, so from our positive Q to the P point is equal to, represented by this vector, R1 vector, and the direction and distance between our negative charge and the particle charge is represented by this R2 vector. So once we determine all the parameters that we need to use, then by using the expression for the Coulomb's law as shown in this equation, whereas the vector of E is equal to 1 divided by 4 pi epsilon naught, summation of I equal to 1 until n, Qi, so R vector of R minus vector of Ri, and divided by its amplitude to the power of 3, with the power of 3. And by solving this expression by considering all the component that we know just now, so we can put that particular component to become this, like this expression. So whereas we have the vector of E, or the vector for the electric field intensity, is equal to 1 divided by 4 pi epsilon naught. For the positive charge, so we have a Q here, positive Q. So this is the vector that represents distance and direction between our positive charge and the test point. So we have R1 vector, so divided by its amplitude with the power of 3, plus, so the second charge is a negative Q, so here we have value of negative Q. So the distance and direction between the negative charge and the test point is represented by this vector, R2 vector, so that we have negative Q multiplied by vector of R2, so divided by the vector of R2, amplitude for the vector of R2 with a power of 3. By put all the parameters that we know, so we can have our expression for the electric field intensity for this case is equal to this expression. Alright, so that's all for now. Should you have any further question or feedback, so please submit it through Ulearn. Alright, good luck and thank you very much.